here's f of x is equal to x cubed plus 3x squared, and here's a graph of that f of x. Of course, we don't have this normally when we do this type of question, but just for practice, I'm going to leave it there. So as we take the derivative and find the critical points and increasing, decreasing behavior, we can compare that to this graph here. So the first thing I'm going to do is find the derivative of f prime of x is equal to 3x squared plus 6x. And I'm going to factorize this. 3x bracket x plus 2. So when is f prime of x equal to 0? Because these are critical numbers. And that's going to be when either 3x is 0 or x plus 2 is 0. And that happens when x is 0 or negative 2. And you can see that here when x is 0, you have where the derivative is 0, or the slope of the tangent line is 0. And when x is negative 2, also you have when the derivative is 0, so horizontal tangent there. Okay, so now I'm going to use my first derivative test to find increasing, decreasing behavior. So I'll draw the number line here, and I'll have a negative 2 and 0, because those are the important points that are splitting up my intervals. So all I have to do is check 3 different intervals, here, here, and here. So let's do that. I'm going to check the sign of f prime of x. So if I were to substitute any number to the left of negative 2, suppose, say, negative 5 or something, then 3 times, so f prime of negative 5, that's going to be negative here. So 3 times negative 5 is going to give you a negative number, negative 15, and minus 5 plus 2 will also be negative. So negative times negative will be positive. So this here is going to be positive, and my graph is going to be increasing in this interval. So you see that here, that's negative 2, and to the left of that, graph is increasing the entire time there. And then between negative 2 and 0, I'll substitute negative 1. That's 3 times negative 1, that's going to be negative, and negative 1 plus 2, and that's going to be positive, so negative times positive is going to be negative. And my graph is going to be decreasing in this interval. And you see that here, the graph between negative 2 and 0 is decreasing. And lastly, I'm going to check to the right of 0. So anything bigger than 0, I'll use 1. 3 times 1 is positive, and 1 plus 2 is also positive, so I'm going to get a positive number there. So the graph is increasing in this interval. And you can see that from this graph here. Now, I want to know if these critical points give me a local maximum or a local minimum. And of course, if the graph is increasing to the left, so it's going up, and then there is the point where you have a horizontal tangent, and then graph is decreasing, then you're going to find that at x equals negative 2, you have a local maximum, as you see here. That's a local maximum. When the graph is decreasing to the left of 0 and increasing to the right of 0, and you're going to get a local minimum when x is 0, as you see on the graph here. This number line is what we're doing here is called the first derivative test. There's an easy way, especially when your derivative is a quadratic like this, which happens a lot in these type of equations or examples. I know that this derivative is a quadratic, and it'll look like a parabola. And because my leading coefficient is positive, my parabola should open up. And when you factorize and solve, you get x equals 0 and negative 2, and that's when my parabola goes through the x-axis. So you are looking at a parabola that does that. And the parabola, the y value of the parabola is above the x-axis, and therefore the positive value there, and then below the x-axis, negative, and then positive. If the leading coefficient were negative, it'll be opposite, and you will get a decreasing, increasing, and decreasing, so backwards. Okay, let's do another example. This is what you saw in class today, but we'll just do the same one again. All right, so it says find the stationary points of the function and determine their nature. So the very first thing you have to do is find the derivative. Y prime is equal to 6x squared plus 6x minus 36. So again, I'm going to factorize this. 6 times x squared plus x minus 6, and I can factorize it even further. 6 times x plus 3 and x minus 2. Okay, so that's my derivative. When is my derivative equal to 0? When x is negative 3 and 2. So I'm going to draw a number line here and mark negative 3 and 2 here. And I'm going to check the sign of f prime. So is f prime positive or negative? Now, I already know that my derivative is it's shaped like a parabola, and the leading coefficient is positive, so I can draw a quadratic or parabola like so, and I know this is going to be positive, negative, and positive here because it's above the x-axis, below the x-axis, and above the x-axis here. Maybe I'll change the color for the bottom part like that. So I know that, and you can do this for your working as well. But let's just check to make sure that what we did was correct. So what should I do? So I need to check y prime of some number to the left of negative 3. So say negative 5. That's going to be 6 times negative 5 plus 3, and then negative 5 minus 2. So 6 is always is positive, and this is going to be negative, and this is going to be negative again. So positive times negative is going to be a positive, and you saw that already here. So graph is going to be increasing to the left of negative 3. What about between negative 3 and 2? Conveniently, 0 is in that interval, so I'll substitute 0 in there. 6 times 0 plus 3 and 0 minus 2. Well, that's going to be a positive times negative, so I know that that's going to be negative, and you saw that there. Graph is decreasing here from negative 3 to 2. Finally, anything greater than 2, I'll try 5 again. 6 times 5 plus 3 times 5 minus 2 plus positive and positive. So of course that will be positive, and you saw that here. Graph is increasing to the right of 2. And because I have a graph that is increasing to the left of negative 3 and decreasing to the right of negative 3, I will have a local max at x equals negative 3, and the graph is decreasing to the left of 2 and increasing to the right of 2, I will get a local minimum at x equals 2. Okay, so let's check. I use Desmos here to look at it. So x equals negative 3, there is a local max. X equals 2, there is a local min, as you saw. Okay?